In this tutorial, we will look at how to implement a basic circuit design in IPKISS. We will design a splitter tree with two levels that is comprised of three connected splitters and two grating couplers. The result is the following circuit with one input and four outputs. To do this, we will use components that are already defined for us in a process design kit. We will use the SciFab PDK, which is included with your IPKISS installation. We will start by using a simple way to build circuits in IPKISS, which is using i3.circuit, which is a Python class included in IPKISS. By defining instances of the class, we can effortlessly construct the circuit and seamlessly establish connections between these instances. i3.circuit automatically generates all the waveguides required to link these instances. In order to create a circuit, we need to define the following things: properties, instances, specifications, and the exposed ports of the circuit that will interface with the outside world. We begin by creating our instances. We're going to use a Python dictionary containing the names of the instances in our circuit as keys. We first need to import the MMI class we will use from the SciFab PDK. Here we have three instances, one for each splitter. Therefore, we add three instances of this MMI to our dictionary. Specifications is a list containing all the layout specifications that apply to each component. We use the i3.place method to position the MMIs relative to the coordinates. In this case, we use two arguments, the component name and the coordinates on the layout. To connect the bends, we use the optical port names of the start and end of the waveguide, and the port names are assigned in the MMI component. Finally, we instantiate the splitter tree. This code block defines and executes the code for visualizing the circuit. It starts by creating an instance of the splitter tree class called splitter tree. This instance represents the actual circuit layout. The next line calls the .layout method of the splitter tree object to generate the corresponding layout representation of the circuit. The .visualize method takes an optional parameter called annotate. By setting annotate equals true, this method will add annotations for all exposed ports on the layout, making it easier to identify the connections and components. Finally, the write GDS2 method is used to save the layout as a GDS2 file. Let's go to the Lucida Academy environment in IPKISS. So we go to Training, Getting Started, Circuit Layout, Tutorials, and we can find the script splittertree.py. All of the code we have seen up to this point is implemented in this script. We see our instances, our specifications, and our main function to run the script. If we run this script, we will get the layout. Now we are going to look at the placement specs and how we can position components. We have a list of functions that can be used to position or reposition the instances. To do this, we simply invoke i3 plus the relevant operation and input the coordinates. First, we will look at i3.place. This allows you to position an instance or its port at a given position and optionally an angle. In this example, we can see an instance with one input port and two output ports. The current specs show the object centered at the origin of the coordinate system. I now want to place this instance with the input port located at coordinates 15, 20. To do this, we use the i3.place function with the specific instance mm1 and its input port, and the new coordinates as the arguments. Extending this further, we can use place relative. This allows you to position the instance or the port of an instance relative to another instance or port of that instance. An offset is applied to place the instance correctly and optionally at an angle. So I have a crossing that is currently centered at the origin. I now want to move this so the output 1 port is rotated 45 degrees relative to the output 1 port of the MMI, with an offset of 5 microns in the vertical direction and 10 microns in the horizontal. To do this, we use i3.placeRelative and first define the instance we want to place, which is the crossing out1 port, followed by the instance we wish to place it relative to, which is the out1 port of the MMI. Next, we pass the coordinates of the offset and finally the angle of rotation. If you would like to add another instance and directly connect it to another, you can use the i3.join method. In this example, we add an additional MMI that is currently centered at the origin. We add i3.join to the specs list and give the new instance and the specific port, in this case MMI2 input 1, and then the instance we would like to couple it with and its specific port. In this example, we have an MMI centered at the origin with the output ports on the positive x-axis. If we want to mirror it horizontally, we can use the i3.fliph method. We can also do this in the vertical direction by using i3.flipv. This time the mirror axis is the x-axis. Here we have an MMI centered at the origin, and now we add a crossing. We can horizontally align a specific port of an instance with another, and we do this by using i3.align. In this case, we want the port out2 of the crossing to be horizontally aligned with port in1 of the MMI. So we add i3.align h to the specs list. Similarly to the last example, we can also align vertically. Here I want port out2 of the crossing to be vertically aligned with port in1 of the MMI. So we add i3.align v to the specs list. Now we switch focus to connections. Once we have our instances aligned, we need to connect them. IPKISS allows for the easy implementation of connectors. Here we will see how to add arguments to this class to customize the waveguides, or use a new class, Connect Manhattan. If multiple connectors share the same properties, such as bend radius and rounding algorithm, then we can pass a list of the ports to create them together. Here we see Manhattan bends connecting the two MMIs. The Connect Manhattan class will route between two ports using only right-angled bends along the path. It also supports the use of control points, which act as anchors that the waveguide must pass through, and these are great for custom routing and obstacle avoidance. We can also connect 2 points through an as simple as possible bend, whether it be arc, U-bend, or an S-bend, depending on the location and angle of the ports. This is implemented in a similar way as Connect Manhattan, but we replace it with i3.connectBend. It is also possible to implement different rounding algorithms to generate adiabatic curves. We can include a specific algorithm in the i3.connect class after defining the bend input outputs and the bend radius. In this example, we define a spline rounding algorithm with i3.spline rounding algorithm, and we have used an adiabatic curve. i3.connectBend can also generate U-bends. The two MMIs in this example are separated only in the y direction, so we just simply add the bend radius and the relevant ports we want to connect. In fact, i3.connectBend can deal with any port orientation. Here we see the MMI at the bottom at an angle relative to the top. We simply define the bend radius and it will make the most appropriate connection. So far, we have seen hard-coded values for different parameters. To get the most value out of using IPKISS, we need to use parametric design principles. For example, we can create a parameter that corresponds to the vertical spacing between the output grating couplers, a common use case is the pitch of a fiber array, and use this to place all the gratings relative to each other. To do this, we need to set up some properties in the class which correspond to all the variables we want to be able to change. These properties can be set when the class is instantiated to configure the class. Here we create a new class called SplitterTree from i3.circuit. Next we define a property named Splitter. There are different restrictions we can place on these properties which restrict the type of objects they can handle. The child cell property is used for the classes we are importing, and the two positive number properties are used to adjust the distance between the splitters and gratings in the circuit. The child cell property is restricted so that it can only take an instance of a P cell, whilst the positive number property must take a positive number. We can now use these spacing in X and Y parameters in our specs list. So we replace the hard-coded values that we used previously. As a hint, the properties must be accessed using self.dot when inside the class. The final ingredient we need to complete the layout of our circuit is to expose some ports to the outside world. We expose the ports using a dictionary where we can also rename the port names for our convenience. Here we define our grating coupler input and output ports. Now we have an exercise for you. In our Lucida Academy material in the PyCharm environment, you can go to Getting Started, Circuit Layout, Exercises, and you will find an exercises.py script. Try to complete all the exercises. If you get stuck, we do have a solution file for you. In the previous section, we designed a splitter tree circuit, and that design is already parametric, with the spacing between various components and the type of splitter used all being parameters. We can extend this approach even further, creating a circuit that is parametric to the number of levels in the splitter tree. To do this, all the instance creation, placement, and routing must be parametric, so that we simply pass in the size of splitter tree we want, and the circuit is built for us. To implement this, we just need to make a few small changes. By nesting a for loop within another for loop, we can iterate through each splitter in each level and add them to our instances dictionary. The good news here is there are very few methods needed for this that we have not already seen. We will use a combination of f-strings and for loops with some basic logic to achieve the desired circuit. We can extend this for both placement and routing specifications. If we look at the top for loop, we see a nested loop that iterates over the number of splitters in each level. The level variable is used to determine the number of splitters in this level. For example, if the level is 1, then there are 2 splitters in this level. We also define x and y coordinates using the parameters spacing x and spacing y as before. This is then appended to the specs list. In the second for loop, we use the modulo operator to check if the splitter variable is even or odd. This will then determine the output port. Finally, we can parameterize based on the number of levels our exposed ports and create and name them using a for loop. It does this by calculating the number of splitters based on the formula 2 times the level minus 1. It then iterates over each splitter, generating port names for each splitter and adding them to the exposed ports dictionary. We can then simply pass the number of levels as a parameter and then visualize the layout. You can find all of this in the Advanced Examples section. So we go to Explore Generalized splittertree.py and we will run the example. Here we've used the number of levels equal to 4, and we see this in the layout. So it's just a simple case of changing the number of levels as the input argument. Let's choose 7, and we simply rerun the script. Using the parametric splitter tree, we can now create a more complicated circuit using bundle routing and control points, as well as some alignment options. To reuse the splitter tree circuit, we first import it from the other script and then rename it to tree. We can use align V and align H to position the crossing in line with existing ports, to reduce the number of bends in the circuit. By providing these specifications to the specs property of i3.circuit, we can constrain the location of the crossing, allowing the placement engine to resolve its coordinates. The waveguide that connects the south port of the crossing with the grating coupler array needs to be routed below the splitter tree, otherwise the waveguides will cross. We achieve this using a control point. In this example, we use i3.h to specify a horizontal coordinate position that the connection must pass through. This point can be defined from the parameters that create the splitter tree, ensuring it will work regardless of the splitter tree size. Lastly, we use i3.connectManhattan bundle. So we create a connections list, which uses list comprehension to dynamically generate the connection pairs. We then use a loop to iterate over a range starting from 2 up to the value of self n levels. This represents the number of levels in the design. We implement the bundled connections using i3.sbend fan out, with an angle of 90 degrees at the start and end of the fan. The pitch refers to the distance between each connection. In this tutorial, we have learned how to define an i3.circuit in code. This includes instances, specifications, parameters, and exposed ports. We then extended this by making a parametric design that created a reusable and reconfigurable circuit. We finished by looking at some advanced layout concepts, including bundle routing, vertical and horizontal alignment, and the implementation of control points. Please visit Lucida Academy for many more interesting examples. If you have any questions, please contact us at support@lucidaphotonics.com.